Hello everyone, this is Dr. Deepanita Chakraborty and I am going to take the first unit from the course Electricity and Magnetism. In this video, we will be seeing about the basics of Gauss law and its application, starting from what is Gaussian surface, what is flux, and how can we define Gauss law, followed by applications of Gauss law. So what is Gaussian surface? Any kind of surface which is closed and which is having uniform distribution of charges can be termed as Gaussian surface. Then the Gauss law is made in Gaussian surface and it relates the electric field at any points on the Gaussian surface with the net charge enclosed on that surface or inside the surface and the flux related to those surfaces. Flux. Flux is a Latin word which means flow. So the number of lines of force crossing per given area or any volume is termed as flux. Suppose if we take a region of square shape or circle shape, anything, the number of lines of forces crossing it, that means if two lines of force is made incident on the square surface and if those two lines come out from that square surface, then the flux is 2. If three lines are incident and only two lines are made to come out, then also the flux will become 2. It should cross that surface. So the number of lines crossing them is termed as flux. So the lines of force or the energy should be perpendicular to the surface. So the velocity of those lines should be perpendicular to the surface. Suppose this is the surface, then it should be perpendicular. The lines of force should be perpendicular. Then only it will come out of it. If they are parallel like this, then it will not come out. It will be going as it is. So it should be perpendicular to them. So the formula for flux is V cos theta into A, that is V vector dot A vector. Then how can we determine the flux of an electric field? For example, if we take a closed region and in that we are considering a smaller space, that is ds, and the electric field is termed as E vector and ds vector is the normal to that plane. So the normal to that plane is ds vector and the electric field, suppose if I take that the charges present in this region is positive, so the electric field is pointed in the outward direction. The angle theta is the angle made between E and ds. The electric field should be constant at all the points as it is a Gaussian surface. Then the electric flux due to through this area ds will be written as E vector dot ds vector, that is eds cos theta, and the total flux will be the integral of the small region. We have to add all those small blocks, so that is done by integral. As it is closed, so we will be using closed integral of d phi. So it will be closed integral E dot ds. The flux of the electric field will always be a scalar quantity and its unit is Newton meter square per coulomb. Then Gauss law. The Gauss law is defined as that the total flux of the electric field over any closed surface is equal to 1 by epsilon naught times the net charge enclosed in the surface. So if this is the enclosed region, then the flux in this region will be 1 by epsilon naught times the net charge enclosed in this region. So if we know any one parameter, if we know the charge, we can determine the flux. If we know the flux, we can determine the electric field strength. So all are interrelated to each other and they are directly proportional to each other. So phi is nothing but closed integral of E dot ds and it's the measure of number of field lines. So from this we can say that the greater the flux, the greater will be the electric field strength. So EDS is proportional to the flux region. Then application of Gauss law. The Gauss law is applied on highly symmetric charge distribution examples and in if the magnitude of E, that is the electric field, should be constant at all points. Only if these two conditions are satisfied, we can apply Gauss law in them. So there are three kinds of symmetry where the Gauss law is applied. One is spherical symmetry, another one is cylindrical, the third one is plane. So this one is the diagram for spherical symmetry, this is for cylindrical, and this is for plane symmetry. So one more small information, that the equation phi is equal to closed integral E dot ds is equal to q by epsilon naught is the integral form of the Gauss law, while the differential form of Gauss law is del dot E, that is divergence of E is equal to q by epsilon naught. Now this table has been made for easy understanding so that you can have a look on this and you can remember what are the electric fields for different symmetry. For example, if the Gaussian surface is an insulated conductor, in an insulated conductor what happens is the charges are completely filled in that conductor. So there is no place for any other thing or any other object inside it. The charges will be rotating in such a way that they will be cancelling each other, because here positive is there, so outer will be negative, and they will be doing some mechanism which will make the net charge inside the insulated conductor as a big zero. So, and as they are already completely filled separately, they are completely filled. So whenever a new charge is coming to enter this one, what will happen is the charges present inside will repel this new charge and will compel it to stay on the outside of the surface itself. It will not allow inside the surface. So the electric field inside the insulated conductor will be a zero, because the charge will reside only outside the insulated conductor and not on inside. Then if we go for uniform charge non-conducting sphere, in this one what happens is, uh, suppose this is the sphere. So three condition is possible. One, we can consider a Gaussian surface inside it. Another one, on the surface of the sphere. And another one is outside the sphere. So outside the sphere. So these three cases are possible. So for the first case, that is outside the surface, let's say that this distance is r. Then in this region, due to the charges which is present inside, I am saying that this is the Gaussian sphere. So the charges will be uniformly distributed in this region also. So this mechanism will be equal to 1 by 4 pi epsilon naught q by r square. When I am taking inside it, then this radius is termed as r, capital R. So it will be 1 by 4 pi epsilon naught q r by r cube. And at the center position, as the capital R will be 0, so the electric field will be also 0. And then if we consider on the surface, then it will be considered as 1 by 4 pi epsilon naught q by capital R square, where this capital R is the radius of the conducting sphere itself, and the small r is the radius of the Gaussian sphere. Similarly, for isolated uniformly charged, the same electric field values will be coming. The slight changes: in case of conducting sphere, no charge will be present outside the Gaussian sphere, but in place of uniformly charged sphere, no charge will be present inside the sphere. So in the second case, that is the electric field inside the sphere, E will be 0 completely, while here it will be inside. Next, for infinite line of charge. In this case, here something interesting is there. So this is the line of charge which is given. Here I am taking that the line of charge is completely positive line of charges. So as it is positive, the electric field from this line of charge will be either in left side or in right side it will be. And there are two flux which can occur in this, because that is a plane of charge. The Gaussian symmetry will be like a cylinder. The Gaussian surface will be considered as the cylinder. So the two surfaces, the two flux region will be one at the curved surface, that is the sides of the cylinder, and the other at the planar surface, that is at the top region and at the bottom region. Now if you see this diagram, the electric field and the normal to the plane, that is ds vector, is perpendicular to each other at the top region and at the bottom region. This will be ds and this will be E vector. So as they are perpendicular to each other, the flux in these two regions, that is top and bottom curves, will be 0. But the electric field and the ds vector are in the same direction in the curved surface, that is on the sides. So only in this region the flux will be acting, and that flux is nothing but E into 2 pi RL. So electric field into, in place of area, we are writing the area of the cylinder, which is nothing but 2 pi r. So from here I can get that E is equal to lambda by 2 pi r, because E is, so phi is equal to q by lambda. So if we equate both, we will get E is equal to lambda by 2 pi epsilon naught r as the formula for the electric field in this case. Then if we go for plane sheet of charge, in that case it will be reversed. In plane sheet of charge, the flux at the top and the bottom region will be having maximum values, as the ds or the dA direction and the direction of the electric field will be same, while the at sides the direction of electric field and the direction of the area will be perpendicular to each other, because this is the sheet here, the plane. So the electric field will be going up and down in this case. So that will be equivalent to the, that will be in same area, same direction as the surface direction. So here for plane sheet of charge, the electric field will be sigma by 2 epsilon naught. And if we take two parallel sheet of charges like this is one sheet and this is one sheet, then we can consider 2 points. One is in between the charges, one is outside the charges. If the sheets are having same charge, that is if both are positive, if I say, then the electric field on this charge will be acting outward here, and here it will be acting outward in this direction. So at this point P1, if I say this is P1, then there will be addition of those two, and if at the middle the plus charge will be coming here and this will be coming here, so this will be E1 minus E2 in the middle point, so that will be 0. But if the charges are opposite, if they are of opposite charges, then if this is a plane of positive and this is a plane of negative charges, then this electric field will be in this direction and it will also be in this direction. So any point which is present here, let me say the electric field due to the positive charge is E1 and the electric field due to the negative charge is E2. So the, for any point in between them, in between the two planes will be, as the directions are same, it will be E1 plus E2. So the direction due to a plane charge is given by sigma by 2 epsilon naught. So when we add these two, it will become sigma by epsilon naught. And if we take any point outside, then as it is a minus charge, the direction will be here, and due to the plus charge, the direction will be in this direction. So E1 minus E2, that will be giving us the answer as 0. So P outside the sheets will be 0 and inside the sheets will be sigma by epsilon naught if the two sheets of charge are of opposite signs. And if we are taking an infinitely charged cylinder, then we have to consider the volume density. So instead of lambda, we'll be considering rho, that is q by pi r square L, remaining the same thing. Here also, the flux will be obtaining at the curved surface and not on the planar surface. That is, at the sides will only be, we will get the electric flux, and we'll be combining these two, and the electric field is obtained as rho capital R square by 2 epsilon naught r. And if the radius of the surface is small, then it can be written as rho capital R by 2 epsilon naught. And for inside, the value is E is equal to rho R by 2 epsilon naught. At the end, we can see that from this video we have learned about Gaussian surface, the flux in an electric field, the definition for Gauss law and how it is related to the electric field, and what are the easy ways to remember the electric fields of different Gaussian symmetry. Thank you.